Hi everyone, today is the fifth week of our series on writing functions over length index vectors, where the goal here is to learn about type index programming. So Haskell has lots and lots of features for doing fun programming with types, and we're exploring that space by writing successive functions, all taken from data.list, and trying to translate them to work over length index vectors. Even though this is the fifth in a series, you don't need to have watched the other videos to get meaning out of this one. The only really key part is that we're using these data type definitions, right? So the idea here is that we have a vec, and this vec is indexed by its length and the type of its elements. And so here we know if we have an empty vector that its length is 0. If we use a cons, then we're going to take some other vector of length n and we're going to produce a vector of length suc n. And so that's where it all starts, and then let's explore what we can do with that. Now today, this week, is going to be all about proofs. So we're going to try to write a function, see that we can't quite write it the way that we want to, and then we end up writing an inductive proof in our Haskell code. I should use proof in quotes, we'll see why. And then that's going to get the function that we want to work in the running time that we want it. Okay, so the key function that we're going to spend the whole video on today is reverse. So let's just take a look at how we would define reverse here. So reverse is going to have this type, right? So this is saying already that the length of the reversed vector is the same as the length of the original vector because we have n and then n. So we're going to get some extra checking to make sure that we don't drop or add elements here in reverse. So let's see, let's try to write reverse the easiest way we can. So reverse of nil is nil. Does that work so far? Yes, it does. Okay, one module loaded, excellent. Now we can try reverse of x cons x's. Well, what does this have to be? Well, this is going to be x after the reverse of x's. So we can say reverse of x's, and then we sort of need to con something on here. And so I'm going to call that snock, and we're going to take snock x. Of course, this is going to fail because we don't know what snock means. So now let's add snock. So snock takes vec na plus an a, and then it's going to give us vec suc na, right? Because we're going to make the vector one element longer. So now let's look. So snock of nil and x, that's just going to be x cons nil. Okay, one module loaded. And now snock of, let's see, y cons y's and x. Well, what is that going to be? That's going to be y const onto y's snock x. So that's going to put x at the end of the list, exactly what we want. And then everyone is happy. Okay, so is that it? No, that would be a very poor video just to only do that much. And that's because this reverse has a terrible, terrible problem. It is quadratic. Right, so if we look at this, if we imagine this input length, this input vector, it has length n. Well, how many steps does reverse take? Well, it's going to recur down reverse one time per element in the list, and then each time it recurs down reverse, it's going to call snock. Now, how much work does snock do? Well, snock once again recurs down the list. So that means that we end up with this 1 plus 2 plus 3 plus 4 plus 5 plus whatever up to n, and that's quadratic. So that's no good. We really shouldn't have to do that. So let's come up with a better way of writing reverse. I'm going to leave this in commented out, but it's not very good. And so instead, let's look at a new reverse. This is going to have the same type, because we got the type right. But instead, this reverse is going to use an accumulator list. So by the way, this runtime problem is just as true of normal lists as it would be of length index vectors. So if you try to write this over lists, don't use snock, right? That's quadratic. It's no good. So here, we're going to try to write reverse. And now, instead of just directly pattern matching, what I'm going to do is I'm going to use a helper function, and I'm going to say go nil, where go is now going to take a vec na. Well, let's actually write the definition of go, and then we'll come back to the type. I think that'll work out better. So the idea here is that we're going to have an accumulator list. So this is the accumulator. If we have no more input, then we're just going to return the accumulator. And if we do have some input, x cons x's, then we just append that to our accumulator while we recur. So we have x cons ac and then x's. And then here, what's happening up here, right, this is the same as saying y's on both sides. So I'll keep that in. We don't get anything. That change, putting the y's here versus not having y, that's called an eta reduction or an eta expansion. So here I have eta expanded because it's maybe a little easier to read. And so the idea here is that as we recur down our list, when we find an element, we're just going to put that onto the accumulator. But if we think about this, this reverses as we go. And then when we run out of input elements, well, now we've built up this reverse list, let's just return it. So this is linear time. That's exactly what we wanted. So this is a big improvement. Again, this would be just as true over normal lists as it is over length index vectors. When we try to compile this, we get a whole lot of gobbledygook. We get the dreaded, terrible P is untouchable error. This is a design mistake in GHC, in my opinion. I guess I take some responsibility for it now because I could have fixed it for a while now, but I haven't myself. But the idea here is that there's this very complicated theory for how we do type inference with GADTs, but that theory is not very much of interest necessarily to Haskellers, and there's this thing called an untouchable variable. What this really means is you're doing a GADT pattern match without a type signature. And so Go here is doing a match on this nil versus cons, and we don't have a type signature, and GHC just can't cope for really good reasons. I don't want to go into the reasons today, but we really don't know how to do this. And when I say we, I mean computer science. It's not just GHC. This is an open problem how to do this well. But the solution is easy. Whenever you see an untouchable error, just add a type signature on your GADT pattern match. So now you have to think, well, what's the correct type signature here? Well, clearly this takes in two vectors. Let's say MA and PA, because I don't know what the relationship is between these and the n, so I don't want to make any assumptions. And it's going to return some vector, but what's the length of the output? Well, the length of the output here is going to be, well, let's see, in the 0 case, we just return one of our arguments, so then it's going to be the same as m. Here, we move one element to the other list and then return. So really what's happening here is that this Go function could also be called rev append, right? We're really sort of appending the second argument reversed onto the first. That's really what's going on here. So actually, the result is going to be the sum of the lengths of the inputs. So I want to say m plus p. And then now when I compile, we get other errors. Could not deduce m plus 0 equals m. Well, that kind of makes sense as an error message, right? Because here, my nil tells me that p is 0, and I'm returning ACK, which means I want to return something of length m, but I'm actually supposed to be returning something of length m plus p. In other words, m plus 0. Do I know that m plus 0 is m? Well, now let's go to a split screen here, and let's find type family. Here we have type family plus. So if we look at the definition of plus right here, I'm going to make this, let's jiggle these windows around a little bit. When I have this plus here, then what I'm defining that 0 plus b is b, but I haven't said anything about b plus 0. And for good reasons, I can't just write that in. That's not going to work out if I just write that in. Again, I don't want to get distracted by that today. Instead, what I need to do down here is to prove that m plus 0 really equals m. So let's see, what can I call this? I can call this plus 0, or maybe m plus 0 to say that the 0 goes on the right. And so what this is this is going to be a proof that for all m plus 0 equals m. And let me put in some parentheses here to make this easier to parse. And that's what I'm going to prove. So I can write m plus 0 equals, and then just for now, let's say undefined. Oh, we don't know what this funny twiddly thing is. I should just go up here, and ooh, it's very small. I need to import data.type.equality, and that gives me this type, which I'll show in GHCI in a moment. Let's also import it down here so I can show what this type is. Okay, so here it is. It has a bunch of instances. That's not what we care about. What we care about is the definition. So here's the definition. Now here, this twiddle, this is also called propositional equality. This propositional equality type is a GADT that says that if we have a witness called REFL at a certain type, it's saying that those two types are equal, right? Notice that we can only construct an element of this twiddly type here when both type indices are the same, A. That's the key piece here. So that means that if I have a witness of this, if I can pattern match against REFL, then I know that m plus 0 equals m. So let's see this in practice here. So what I want to do is I want to say case m plus 0 of REFL. And then now that I've pattern matched on REFL, we're going to learn that m and m plus 0 are the same, and then this should be accepted. So let's see what happens when we try to compile this. Not in scope, REFL. Oh, whoops. No, don't do that. We need the constructor. Okay. Now we're going to get something probably more interesting. Oh, it still could not deduce this. But if we now look in the context, now we know that m0 is equal to m0 plus 0. And that's because when we type this m plus 0, we don't know what m we wish to prove about. So we need to specify that. So I'm going to say at m to say, oh, well, here I want not just any m to equal, or not just any m plus 0 to equal m, but I want it for this particular m. So for this to work, I also need to use scope type variables. So then we need to say for all m p a, it looks like. And now let me try to run this. Oh, did I mean to enable type applications? Well, surely I did. So let's put in another one. Whoops. Don't know how to spell my own extension. Let's see here. Okay, so now what do we have? Aha. So now I've compiled, and then when I look, whoops, I want to do that. Now the first problem goes away, and now I'm left with a second problem. So here, could not deduce m plus suc n1 equals suc of m plus n1. This has very much the same flavor. When the suc is on the left of the plus, I can reduce. But if the suc is on the right of the plus, as we see here, I don't yet know that's true. And so now I need to have a new proof, m plus suc. So now for all m, and now we have n again. So now we're going to say m plus suc n is the same thing as suc of m plus n. And then for now, we will fill these in, but not yet. We're going to say that this is undefined. And so now we try to run. Now it says, oh, this type is terribly ambiguous. And that's because m and n are used only under the type function plus. We can't infer what m and n are. That problem is not up here because m over here is not under a type function. But that's fine. We can have ambiguous types. There is a proposal, an accepted proposal, that allows me to mark this per definition, which would be much better, but we don't have that implemented yet. Okay, so I've fixed that problem. And now what do we have? Well, we're going to have the same problem that we saw before in that we don't know. Oh, well, I haven't used it, so that's why it's not there. So I could say case m plus suc of REFL. And now if I try to compile, we still have the problem. But if I look down here, now I know that this relationship holds. I can move this suc from the right of a plus out to before the plus, but I don't know on what arguments. So here I can tell you what arguments they are. It's m and it's p. And so now if I try to compile, what do we have? Oh no, it's not m plus p exactly. That's slightly wrong. Because here, what I really wanted to do is, m is right, but I've pattern matched, and I really want it to be on the length of x's, which is sort of pred of p, but I don't have a pred operator, so that's not going to really work out. So what I need to now say is this x's, I need to give that the type associated with this x's a name. And we don't have an easy way of doing that, at least not in 8.10. There's been some innovations here since, but let's not get distracted by that right now. So here, what do I want to say? I want to say this x's, this is going to have type vec p pred of a. And so now that's going to bind this p pred type variable to the length of this x's. And this is the thing that I need to pass in here. Aha. Okay, one module loaded. Excellent. So this is a bit painful having to do this, and I believe, I don't want to experiment with it right now, but I believe what we'll be able to do in today's GHC is, let me comment that line out, and instead we should be able to write something like this, right? Because in my cons operator actually tells me what this is, and I'll be able to bind this sort of using a type application on the left. Thanks to several folks at Obsidian Systems who have implemented this feature. John Erickson is sort of the biggest contributor there, but Cale Gibbard also contributed. Madeline Haraj did as well. So we don't, again, I don't have this sort of running right now. I'm not going to demonstrate it, but this should work in head. But we're not going to do that. We're going to go back to this with a sort of clunky type signature. Okay, so one module loaded. Excellent. Now let's go back and try to fill in these proofs. Well, what are we going to write here? It's tempting just to write REFL, but now I've just sort of moved the bubble behind the film a little bit, right? I still can't match m with m plus 0. If this worked, my original program would have worked. And so, can't quite do that. Instead, I need to do an inductive proof. But what am I going to induct on? I need to sort of take this apart, and I can't really do that in type. So what I need here is I need something to pattern match on, and that's going to be my singleton. So instead of just taking an m, I need to take now an SNAT m, which is going to then allow me to write this proof. So this m plus 0 here, now if that's 0, well now we have 0 plus 0, and I know how to reduce that, and that's going to work out nicely. Oh, what's gone wrong here? Oh, now my usage site is no good. So let's just for now put undefined. We'll fix it in a minute. Okay, one module loaded. Excellent. And then now my recursive case. So here I'm going to have s_suck n. Well, what's that going to be? If I just say REFL, again, I haven't really done it. I have to use my induction hypothesis. So my induction hypothesis here is going to be case m plus 0 of n. That's this number that's one smaller than m. And if that was REFL, then I can prove that the overall thing is REFL. Hooray. Okay. So now I've written my little proof of m plus 0. Now let's return to this problem here. I actually need to know the length of this initial vector here in order to be able to proceed. The good news is that that length starts at 0 and it only increases. So I can make SNAT m an extra parameter to my go function, and now not only start with nil, but start with S0. And so here I can just call this m, and it's going to be m at the term level instead of m at the type level. And now I can pass m here, and let's see, when I recur, I just pass suck of m. Let's give that a try. Yes, that works. Okay, so let me just recap slightly here. So what's going on here is my go function now not only needs to take this, this accumulator, but we need to know the length of the accumulator. Luckily, that's really easy to do, and we need to know it in a singleton-y way so that we have it at both runtime and compile time. And then now we can have this nice proof of m plus 0 where I pass both the type level m and the term level m into m plus 0. But actually at this point the type level m becomes redundant because I can infer that. And so I can just get away with the term level m. Okay, so I fixed one undefined up here, but now we have another one. This is also going to require an inductive proof. Interestingly, though, it only requires the inductive proof over m, not n, or the singleton over m, not n, because that's where we're doing induction. We're doing induction only on m. So here we're going to S0. Well, if m is 0, let's call up the type family here again. Let's look at it. So if m is 0, then we're in the 0 plus case, and we just return the other piece. So let's try this. So if I say REFL here, is that going to work? No, not quite. Now we could not match, let's take a look at this, blobbity blobbity blah with A equals B in the pattern REFL. What's going on here? This isn't what I expected. Oh, we're down here. Let's just say undefined. I don't want to be down here. Oh, okay. This works, right? Because here what's happened now is I've learned that m is 0, so I have 0 plus suck n on the left. According to this rule, that just equals suck n. And then over here, I have suck of 0 plus n, but 0 plus n is just n, so this is suck n equals suck n. Hooray, success. In the suck case over here, so this is going to be, I'll call this m prime. What can I do? Well, again, just saying REFL doesn't work. I have to recur or use the induction hypothesis, same thing. So if I say case m plus suck, and then now what am I going to pass? I'm going to pass m prime And then I do this, oh, and now we're gonna have other problems because here I know that m prime is gonna be this first argument, but I haven't said what the other one should be. It should be that same n. So I have to use a type application. Oh, not there. I have to use it here, somewhat confusingly. Oh, no, that's not quite right either. So let's look at the error just for a sec so we can see what mistake I made. So here I've confused my n and my m because this n that I'm passing to my recursive occurrence is actually getting instantiated for m here. I don't want that to happen. So instead, I'm going to rewrite this to move my n argument after the snat. So I can do that by writing it this way. Phooey, that's not going to work with scope type variables because scope type variables only snaffles these first arguments that are all the way up at the top. So this just isn't going to work. Blarg. What's going on here? Emacs. Don't fail me now, Emacs. Come on, Emacs. Okay, let's not try to undo again. Instead, I'm going to say for all nm here because n is going to be the interesting one to pass. So I want that type argument first. Okay, and now I'm going to end up with problems down here because I reversed the order of my arguments, so I have to also reverse them here. Hooray! Okay, everything is now working. So I have my little inductive proof that suck on the right can be extracted. That's excellent. And now all I have to do is provide the right thing. But that's really easy. It's just this same snat. Hooray! So now I can pass m in, and all is good. And once again, I can get rid of this extra type parameter because we can infer that. This other one, this n parameter, I can't infer. There's nothing to infer it from. Okay, do I declare victory? Not quite. And that's because now every step in Go, I have to do this proof. And if we look at these proofs, well, to evaluate this to ruffle, I have to once again walk all the way down. I've taken my quadratic algorithm, rewritten it to be linear, and then now because of proofs, it has to be quadratic again. This is very sad. And I don't have a great solution, but I do have a good solution. And the good solution is very naughty. But it looks like this. We're going to say that this proof always terminates. And we're going to say that by saying m plus 0 of anything for all m plus 0 of m is just equal to ruffle. So let's see what GHC makes of that. Well, it's going to say that these don't have the same type. We keep trying this and it keeps not working. But now I take out a sledgehammer. And, oh, here, variable not in scope, blah. That's not in scope for a good reason. But sometimes we have to play with fire. Okay, one module loaded. Oh, rule m plus 0 may never fire because of inlining. So let's just not inline the thing. No inline m plus 0 because we want the rule to fire. Okay, so those of you who have never seen rules, what this rule says is while we're optimizing our program, if I ever see m plus 0 applied to anything for all m, then just rewrite it to unsafe coercive ruffle. Unsafe coercive, of course, doesn't compute at all, so then we just get the ruffle out and everything is happy. What this rule is really saying is because, of course, this function can only return ruffle. There's only one constructor of this twiddly type. So what this rule is really saying is that m plus 0 always terminates. How do I know it always terminates? Well, I sort of look at it and say, oh, every time it recurs on something smaller, and we're not going to have an infinite type, or an infinite term here. But what I really am doing is, I, as the programmer, is saying, I know better than GHC. GHC is trying to make sure that I'm all safe, and I'm actually going to say, meh, I don't actually return undefined anywhere. This is going to be safe. And so there's a small risk here, but we've still won big time over not having all of these checks. So of course we have to do the same in the suck case. So I'm just going to do this same trick again. No inline m plus suck. M, excuse me. And then I have to write my rules here. M plus suck. So now for all m plus suck of m equals unsafe coerce ruffle. And I expect there's probably going to be something about, oh, that's interesting. It doesn't report ambiguity. I guess it's very clever. So here, now I've said that this suck one also always terminates. But the good news is that now when I run my program through the optimizer, it won't take quadratic time anymore. and that's because it never evaluates this. This becomes ruffle, then we see case ruffle of ruffle. The optimizer just says, well, that's very silly, and tosses it out, and we're just left with returning the accumulator. It works out very, very nicely in practice. Okay, that was a long tour through here, but it does take a lot of steps to do this with reverse. So here we see some of the slightly dark underbelly of programming with types, in that we do sometimes have to work harder, and we have to be thoughtful as we're working harder not to introduce inefficiencies. One of the beautiful things about Haskell, though, is that Haskell has things like these rewrite rules, which allow us to assert termination in this way. In other languages, there may be other tricks about irrelevance and erasability, and there are a few other tricks that we can apply. But sometimes we can't really get around it, and we don't have these rewrite rules, and we can't just skip to the chase. Anyway, I hope that this has been interesting. Thanks very much for watching. Bye.